Exam was postponed from before break till January 7th. In class on the 6th, we're going to be going over this. And I did put it on Schoology before break or at the beginning of break. Sent an email through Schoology, or a message, I guess, that this was available, but we will be going over it in class. So as a quick heads up, these solutions, this video, everything will be in this folder here. Obviously, if you're watching the video, you know that. But also, that folder happens to have the unit guides, which are a description of what you need to know for each topic. And this was the initial exam information sheet that I handed out. Okay. So, this one, the first problem is asking about a drone. It's up here. It's going to go down this field, which I'm saying is 100-meter length. How much time will it take if it starts from rest and accelerates at 2 meters per second squared? So, in this case, we go back to our linear motion formula. We're going to use the simple one without an initial velocity. So it's something like that. I know the distance, I know the acceleration, I need to find the time, so I've got to rearrange that. 100 meters over 1 meter per second squared equals t squared. So I take the square root of all that, and that comes out to be 10 seconds. So then it's asking about the final velocity of the drone as it reaches that mark. Well, it's accelerating the whole time and it starts from rest. So I'm going to use a version of this formula. So final velocity minus initial velocity is equal to acceleration times time. My initial velocity is 0. I'm accelerating at this rate for 10 seconds, so that's a final velocity of 20 meters per second. I ended up graphing this a little bit low. I screwed up initially with how I did one of the points. You can see up there I sort of whited it out. So it says we did very early in the semester a bounce height versus drop height lab, and I gave you some data for that. So the goal would be bounce height versus drop height. So if you have something as a function of something else, dependent variable, independent variable down here, you want to scale things consistently. The y-axis and the x-axis don't have to be the same scaling, but they each need to be consistent. So for example, I wouldn't have this go 0 to 10, then 10 to 50, and then 50 to 100, something like that. So I've got this labeled. This ended up being a curve. So my curve here should have been probably a little bit steeper because it's below these last two dots, or last two data points. Make sure when you plot the data points, it's really clear to me where you plot them. And in this case, it says determine the slope of a line if it's not a curve and write an equation. Well, this is a curve, so you don't have to do that. But you should be able to make a graph with a straight line, come up with a slope, come up with a complete equation. In this case, if it were a straight line, it would be bounce height equals whatever the slope we would determine times drop height. And if it starts at 0, 0, we have no y-intercept. In this case, we can't get a slope because it's continuously changing. So if I make an estimation for how high the ball will bounce, if it's dropped from 30 centimeters is around here, it looks like around 9 centimeters for bounce height. And this is a quadratic relationship. Excuse me. Early in the year, we had all those different mathematical and graphical relationships. Number 3 here, in the physics cannonball chute. So this is a projectile motion problem, similar to ones we had before break. It says determine the time for the cannonball to hit the ground. So in this case, I need to think vertically. This is 1/2 at squared. I know the height is 60 meters. Acceleration due to gravity is 9.8 meters per second squared. So again, I've got to rearrange this. Half times 9.8 is 4.9, so I take 60 divided by 4.9. That's equal to t squared. And then I take the square root of that, and that's around 3.5 seconds. So if I determine the launch speed, horizontal speed does not change. So here, actually I should have just written this as VH is equal to delta x over delta t. So I don't know why I wrote it this way. But 75 meters divided by 3.5 seconds, it's around 21.4 meters per second. And then, at what rate does the cannonball's horizontal speed change each second? It does not. So horizontal speed does not change because there's nothing causing it to change. There's no acceleration due to gravity acting horizontally. So the horizontal speed just before it hits the ground is still 21.4 meters per second. At what rate does the vertical speed change each second? That's 9.8 meters per second every second. And what's the vertical speed just before hitting the ground? Again, this is a version of this, which we also used up here. So final velocity is acceleration times time, since there's no initial velocity. 9.8 times 3.5 means we end up around 34.3 meters per second. If the cannonball was launched from a taller cliff, but you still wanted to hit the target 75 meters away, would you launch the cannonball at higher or lower, the same speed? So if it's launched from a taller cliff, it's going to be in the air for more time, so you would need a lower horizontal speed. 4 is looking at the graph of a velocity time graph. We've done this quite a bit the last couple weeks before break, actually for quite a bit of time. So it's the first thing is asking the acceleration at this point at 2 seconds of this solid line. Well, at that point, the slope is 0, so there's no acceleration. The slope of velocity time graph is the acceleration. Part B, the slope is the acceleration again, so we're only looking at this region. So this is what we would call in math a piecewise function. The first part and the second part seem very different from each other. So to get the slope of the second part, I take the final velocity minus the initial velocity and divide it by the time interval. So the time interval is only 4 seconds, and the change in velocity is 8 meters per second. So the acceleration is 2 meters per second squared. How far does the skier move during the 8-second part of the trip? So there's a couple ways you could do this. You got to get the area of this graph. So what I did is I took this from 0 to 8 seconds. The initial velocity was 2 meters per second. So I multiplied 2 meters per second times 8 seconds to get that area of that rectangle. That was 16 meters. And I took the area of this triangle. That area of a triangle is 1/2 height times base. So 1/2, 8, because I'm going from 2 to 10, times 4. It was only 4 seconds. So 8 minus 4 seconds is 4. 8 times 4 is 32, times 1/2 is 16. So that actually came out to 32 meters, which is interesting. Now let's say there's another skier, and they're starting at the same spot at 0 seconds. His motion shown by the dash line. First question was, does the skier travel further, the same distance, or less? I'm going to get the area of that graph by using 1/2 base times height, so that's 1/2, 8 seconds times the final velocity of 10 meters per second, so that's 40 meters. So this new skier traveled farther. If I want to get the acceleration of this, I would get the slope of the graph, and that slope is less steep than the slope here. So the overall acceleration of this second skier is less than the first skier's acceleration at 6 seconds. Hopefully those help. Hopefully those are things you can at least sort of refresh your memory regarding the materials from first semester.